Hi, and welcome to today's webinar about how to build payment systems that scale to infinity by Cockroach Labs. I'm Eric Koslow. I'm an editor for InfoQ with a main focus on application security, Java, and managed runtimes. And we've published quite a few news articles about Cockroach Labs over the last several years, from their recent serverless offering going GA to their reports on CPU performance in cloud operations. Now, the webinar format for today is going to be a little different than other webinars that you've attended previously. Instead of slides, we're going to have a bit of a fireside chat where the team talks about how payment systems work, what different traditional payment systems look like, and how to build systems that can meet all of the above requirements. And we walked through this format with them previously as a preparation, and I was actually pretty impressed at the scope of what Cockroach Labs has done over the last several years. Now, in this chat, we'll have Keith McClellan from Cockroach Labs leading the discussion with Alex Lunev. And we'll send a copy of the recording within a day, just in case you want to rewatch or share. And there aren't many slides, but we'll share those also. Now, Keith McClellan is a director of partner solutions engineering at Cockroach Labs. And prior to Cockroach Labs, he held technical leadership positions in cloud native and big data companies, including DataStax, Mesosphere, which is now D2iQ, and Platfora. And Alex Lunev is a director of engineering at Cockroach Labs. And prior to joining Cockroach Labs, he spent 16 years building payment systems at Square, BlackRock, and Vero. Now, for attendees, please write any questions that you have in the chat. And Keith and Alex will be fielding questions live as they come in, but we'll also take some time at the end to answer any remaining questions that come in at the end of the discussion. Now, Keith and Alex, we look forward to hearing your conversation.
Thanks, Eric. Appreciate it. Alex, how's it going today?
It's good. How are you, Keith?
I'm doing great, man. So we're here to talk about CockroachDB for building payment processing services. CockroachDB is used in the financial services market in quite a number of different spots. So we have some references here. I believe a PDF of the slides is going to be shared with the participants of the webinar after the fact. So you'll be able to click on those links and learn a little bit more about how folks use CockroachDB to help solve some of these problems we're going to be talking about here today. So Alex, why don't we just kind of jump into it? Do you mind giving me a little bit of your history and background in building payment processing systems?
Sure, Keith. So I've been working in the financial technology space for the last 16 years before joining Cockroach Labs. I started out building order management and trading systems at BlackRock, where they're not really considered to be payment systems, but at the end of the day, when you're processing stock transactions or bond transactions, or you're processing credit card payments, the needs of the applications are quite similar in what you have to actually handle. After BlackRock, I moved on to Square, where I spent 3 years working on the core payments team. We were responsible for all of merchant settlement at Square, and also all of the internal payment APIs and microservices that powered the payment systems at Square. And after that, I spent a couple of years working at Varo, building all of the technology for the new bank.
That's awesome. So how different was BlackRock kind of from Square, right? Does seem like, like a trading platform versus a payment processing platform. Like, I would expect there would be some differences, but like, how was it different? How was moving to Square similar to what you were doing at BlackRock?
It's interesting. Like, if you think about it, the businesses are totally different and the requirements of the businesses are totally different, but the technology needs of what you actually have to do are quite similar to each other. At the end of the day, for BlackRock, we had to process stock transactions. And if you think about it, a stock transaction is you place an order to buy some IBM, you have to send it to a counterparty, whether it's a broker dealer or directly to an exchange, and get that order filled, process all of the executions coming back, and then book the trades that impact your positions off the back of those executions. And you have to do that all correctly and reliably, and you have to guarantee a significant uptime for the system, because the equity markets are global, so there's always equity trading going on. Well, maybe except for like a small window on Sunday somewhere where all of the markets across the world are shut. And so you have actually like a maintenance window that you can squeeze in and do some things to your system without necessarily impacting your business. Square is actually quite different in that way, where there is no natural maintenance window for an applications. There's always a credit card payment going on somewhere, like somebody's buying gas somewhere at 3 a.m. on the interstate somewhere, or somebody's buying a burrito or something like that. And so there's actually like a harder requirement where the system has to be always up and available to process credit card transactions. And it's kind of like the same thing, you know, whether you're processing one transaction or the other, the systems that you built for it have to be correct, stable, and available.
So how do you handle not having a natural maintenance window at Square differently than you handled having a natural maintenance window at BlackRock?
That's an interesting question. So at BlackRock, we had a natural maintenance window. So we did all of our maintenance in that window, and we can actually take the system down for an hour and perform releases and upgrades. And that worked really well for us because we could take that time to do things slowly and correctly. And we didn't really have to worry about the fact that, you know, like the business is down and nobody's able to do anything. At Square, it was very different because there was no natural time you could actually take the system down and guarantee the fact that nobody's going to be processing the payment out there somewhere in the wild. And so therefore, we had to actually architecture our systems for being always available and always running so that we could always guarantee to take a payment. If you think about how the system was built to begin with, the main ethos of the system was that doesn't really matter what's going on. We just have to be always able to accept the payment. That's our number one priority. And if that works, then it doesn't really matter that, hey, maybe like your dashboard to view payments is not loading, or hey, maybe like some other part of the application is not working. Like the main use case for people is that, you know, like you have 100 of, not angry, but maybe like hungry people outside of your food truck, and they want burritos. And if you tell them that, you know, like, hey, like we can't give you guys burritos because our payment system is not working, you're going to have a mini riot on your hands. And so therefore, our real core value that we provided to our customers is always being able to be up and to be able to accept those payments and to architect the systems to be able to do that. And what really that entailed is that we had to use legacy database technologies that we had available to us. So in this case, it was MySQL, and build really weird application level solutions around it so that we can build a fully available, highly scalable application that would be active in multiple data centers. And we had to build a complex layer of logic at the application layer that would do a lot of magical routing around the different data centers that we had and kind of bake it all together so it looks like one system, but actually underneath the covers, it's two fully independent systems that are running in different data centers. And depending on where you were, it would route to the correct one, and it would be able to process those transactions in that data center. And then when we have to do maintenance, we would have to say like, okay, like let's move all of our flows from one data center to another, bring the system down on that data center, perform maintenance on it, and then bring it back up, and then do the reverse for the other data center. So it's interesting that, you know, technology is significantly evolved now. And so now if you actually have systems that can support natively running across multiple data centers and be able to accept reads and writes across multiple data centers, you can actually architect this a lot better with things like CockroachDB, which actually has full multi-data center support where you can accept writes in any given data center, and logically to the application, it appears as one database rather than actually pretending in the application layer that you have two applications that are running independently in two data centers, but are always active.
So I think you touched on one of your big challenges around being able to manage kind of those migrations, but what other big challenges did you see when you were building those systems?
That's an interesting question. So one of the challenges that we see is, if you think about maintenance of the application, one of the core challenges is that, well, how do you actually change the schema of your application at the database? A lot of times, if you think about it, not many application technologies support online schema changes. So for example, at BlackRock, when we used to run schema changes, you know, like shut the apps down, run some schema changes, then bring them back up, and then hope it all works. And then really it's making sure that maybe if we can actually step back about and think about, like how you build an application and walk into some of the challenges that way. And so if you think about it, when you first start building an application, you try to imagine the simplest possible use case that you need to handle. And so if you have a simple use case, you can build a data model, you can deploy it on a single MySQL server, Postgres server, or something like that, boot up some system, run it, and that works quite well. You can process some number of transactions a second. You can guarantee that they're relatively correct because you're using the database internal transaction logic to guarantee correctness at the system level, and you're happy. And so you've kind of addressed your main concerns of correctness and scalability. But then all of a sudden, your business takes off. And now instead of processing 10 transactions a second, your business needs to process 1,000 transactions a second. So what do? Well, you go out and you say like, okay, I'm gonna have to buy a bigger server to host my Postgres instance or my SQL instance and hope that works. Okay, and then your business grows a little bit more. And then all of a sudden you say like, well, okay, well, that 32 core machine we had is no longer enough to handle our load. We'll have to buy a bigger one. And then you have to buy a bigger one. And then you have to buy a bigger one. And so, for example, when I worked at BlackRock, it felt like every year there was like a truck showing up at the data center that was just delivering an ever larger machine to run our database. But then eventually, like as you and I both know, that doesn't really work because at some point in time, you've reached the size of the machine that you can actually buy in order to support your business. And then your payments business has grown beyond that. And then what do? Well, in some cases, what we've done for some applications is we went to some kind of like NoSQL solution. And it's like, great, like we have this NoSQL solution, whether it's Cassandra or something Bigtable related or Dynamo, it works really nice. But back in the 2010s, they didn't really have transactions or all kinds of reliability guarantees. So now you're kind of like trying to reinvent two-phase commit in your application. And having done that, like, yeah, you could probably do that, but then you're spending a year building the two-phase commit protocol in your application rather than building a valuable business application that you can deliver to your customers. And while it's
yeah, and isn't there like an auditability concern there too, right? Because these are financial transactions, right? Like somebody needs to be able to validate them historically, and wouldn't that cause a problem, something you'd have to build into your app to support that as well?
Yeah, so typically the way that works is you have to run some kind of reconciliation service on your payments application. So typically what that involves is that you have if you kind of like think about it, you have money coming into the organization and you have money coming out of an organization. And at the macro level, you have to build a system that is able to tie all of that money together so that you can understand that, like, hey, I'm I am processing $100 credit card transactions on behalf of this customer. And then I, as a corporation, I am gonna take $2.75 as a fee to process that transaction. And that's gonna go into my corporate accounts to do that. Then as I process this transaction, I'm also gonna pay a certain amount of fees to the processor on the other side, whether it's like Amex or Visa or whoever represents them in that case, and pay them some money. And so now I owe $97.25 to the person I processed the transaction for. I have some money in my account. I then have to have money coming in from the actual network, whether it's Amex or whoever is representing them. In this case, like it's usually called the payment acquirer, to give me money back. But they're not going to give me $100. They're going to give me $100 minus their fees. And then I have to kind of like reconcile all of that together and then make sure that all of this ties out for, like let's say 1 million to 10 million to 100 million or whatever is the number of credit card payment transactions that I'm going to process in a day, so that I can make sure that things are traveling correctly. And then if you think about it, like to build that all together in a system that works and is easily auditable is no easy feat. And we can, for example, see in the wild now that there's a company that's undergoing like a critical event right now where they looked at their books and they're like, well, we have no idea where the money went. It like went somewhere and nobody knows.
So is it safe to say that trying to build those types of capabilities into your app instead of having in the database layer is fundamentally kind of a riskier proposition for business?
I would say the one way you can think about building payments applications is that if your payments are kind of like the lifeblood of any business, because if you think about it, if your business is not generating money, then is it really a business? And so if you are in the e-commerce space, or in the payments processing space, or whatever the space is, at some point in time, you're having to deal with money flows in, money flows out. And so being able to correctly record those and be confident that you have a correct system of record is very, very important. But that's just kind of like one piece of the puzzle. The other piece of the puzzle is that your system of record has to fit into the general ecosystem of your application. And that's where kind of like, a lot of interesting technologies come into play. And so one of the things that you can think about is that, like, okay, well, you have a payment system, but that payment system doesn't exist by itself. It has to exist within the ecosystem of your product. And so you have to connect it to all other kinds of systems. You have to connect it to this reconciliation system that we talked about. You have to connect it to your fraud checking system to make sure that people are not running fraudulent credit cards through your business or fraudulent transactions. You have to connect it to reporting applications. You have to connect it to all kinds of things. And then once you start thinking about it, well, now you have to get application developers to build all that stuff. But then you run into these problems where, okay, like you've connected it to system X. How do you know that system X has the same view of the payments information as your true system of record? Well, now all of a sudden you're kind of like building two-phase commit again. On top of like some event bus, whether you're using AWS like SQS or SNS, or you're using Google's PubSub or something, like you have to kind of guarantee that the events that you're publishing to those systems, to connect them all together, they tie out between the systems. And doing that by yourself is, you'll build it and it'll kind of mostly work until it doesn't. And then all of a sudden you'll find like thousands of transactions missing somewhere, and somebody will have to spend 2 months auditing all the systems to try to find all the gaps in them. And so one of the things that's really nice about modern database technologies like CockroachDB is they offer technologies like CDC, where you can guarantee that you can actually emit all of the events onto some message bus transactionally, and then get them over to your other system and have a relative degree of confidence that all these systems that you're trying to keep in sync are actually correct and have the requisite data in them.
So, you're touching on something I was about to ask, but that's great. I'm glad we're both thinking in the kind of the same direction. How do things change when you have a single system that you can use as kind of the center for this, where you're not having to manually manage HA and DR, you're not having to manage do kind of external consistency management across sites or kind of manual sharding types of activities? How does that change the way you design these types of systems?
Yeah, that's an interesting question. And one of the things that we were talking about earlier, and we didn't really quite get to finish that train of thought, is that at some point in time, once you grow too large for a single machine, you have to move into this world of, well, now in order to support my transaction processing, I have to shard my system. And as a person that has sharded MySQL many times over, the one feeling I was left with is I never really want to do that again. Like sharding MySQL is really fun the first time, and it's really not fun the 12th time you do it, or like the 15th time, and when you have to do it every 6 months over and over again. And I think like one of the things that's really great about systems like CockroachDB is it's auto sharding and auto scalable for you. You can just increase your workload size and add some machines, and the system will kind of just figure out how to spread the data across that machine. And once you have a system like that, you can start making interesting decisions. Typically, in the way that we've built these applications in the past, is that you had your transactions processing application, which was very geared towards transaction processing. You then tended to have your application and set of databases that were responsible for showing those transactions to your customers, and then doing something else with those transactions, and then doing something else with those transactions. And you typically did that for reliability concerns because you were worried that your reporting application or your user-facing application might overwhelm the transaction processing application and interfere with it. But now if you have a database that you can kind of grow and scale dynamically and can actually absorb that load for you and run across many, many machines, now you can think about it, well, actually, do I need to move this data over there and keep these applications in sync? Or maybe I can actually run multiple of these applications on a single database. And you can kind of see some trends reversing where previously everybody was always like, okay, like we're going to have this microservices environment where every application gets its own dedicated database, and we run like one small Postgres here, one small Postgres here, one small Postgres there, where you can actually reconsider that and say that, like, hey, maybe we'll actually run a larger cluster of a modern database technology that can scale with us, and we can connect multiple applications to it because, well, like the database can actually support that and mediate that load, and we're not as worried about it going down and affecting a critical part of our business.
So doesn't that require you to have very different performance requirements out of the baseline system though?
It does. Like if you think about it, transactions processing is very write heavy. Like a lifetime of a stock transactions or a payment transaction is that you'll write it and read it as part of processing. So it's kind of like a 1-to-1 ratio. You'll read it out of the database, apply some state to it, write it back down, write it back down, write it back down. But you're not running massive amounts of read queries on it because, well, like once the payment happened, like nobody really cares about it unless like somebody comes in and wants to complain about a service that you provided and said, hey, well, like this burrito was bad that you gave to me, like give me my money back. Okay, like now somebody has to go look it up, query it, and like refund you your money and do some more processing. But at the end of it, so transactions processing very write heavy, but then all the dashboards that you would show the user that shows them, hey, this is your total transaction processing volume for the day, you've sold this many burritos, you did this many things, like that's all very read heavy. And so you're right, you have to mix your very read heavy workloads with your very write heavy workloads into one system. But if you have a scalable system, like that will generally work, where previously you might have wanted to separate them out.
I feel like you might be hungry for lunch. You've mentioned burritos a number of times. Did you know that if you Google CockroachDB and burrito together, you get a link to the use case for our new trigram indexes? Because that was the demo app that the engineer that wrote the blog post used.
I did not know that, but that's interesting. Burrito is definitely my favorite form of food, though. I feel like everything can be made better through the burrito form.
I 100% agree. So let's kind of pivot a little bit and talk maybe around the security and encryption impacts of building these types of payment processing systems, both using the old methodology where you were kind of cobbling a bunch of systems together versus using like a centralized distributed SQL database like CockroachDB.
Yeah, I think it's an interesting question. At the end of the day, you have to think of a lot of data that you handle in financial applications as toxic data. You have to handle it, but you really kind of want to stay away from it because it just has a lot of information where if that information ever got compromised, it would present an unnatural amount of problems for your business. And then there's a lot of standards that control how that data gets controlled and accessed. Like the easiest one to talk about is PCI. Everything that you do for payments processing, specifically credit card transactions, is governed by that. And so whether you expose or have access to that data very much drives how you have to build those applications and how you have to figure out and isolate that data from the rest of your processing. And so I feel like in some ways, you see people do many different things in this space. The simplest thing you can do is you could just change your database schema and say that, like, hey, we're going to have a payments table, and this payments table is going to have a section of data which has, I don't know, metadata about the payments, which we don't really care to encrypt because it's not proprietary. And then there's a bunch of payments information here that is, and we want to encrypt that information. And then we will use some external provider like a KMS, and we will encrypt that data and we'll just store it in our database. And what you end up having when you do something like that is you end up building all of these applications. You'll build your user service, you'll build your payment processing service, like a balance service, some other service. And then all of a sudden you kind of like look at it and you have like an encrypted column here, an encrypted column there. And then you're like, oh, well, we were a single AWS deployment up until this point. And now we want to deploy a disaster recovery site in another AWS region. Oh, and I just found out that KMS doesn't really let you share keys across regions. So now I have to go find out how I'm going to make all of this work across like 10 different microservices and get a second set of keys in there and re-encrypt everything. And like, it sounds like a contrived example, but we actually had to do this at a company I worked at. And it's a ginormous pain. And so one of the things that's really helpful is that if you have to think about it, like how do you isolate all of the information that you encrypt in the central service? And so if you could actually do that, and instead of saving, for example, the encrypted data like as encrypted cryptograms in your database, you could say maybe like pointers to encrypted data and keep the encrypted data in some central service or a central table in your database. Then all of a sudden you can actually say like, well, actually all of my toxic and encrypted stuff in this like one place. I'm going to watch this one place really careful. And when I have to rotate keys, I only have to really do it in that one place. And that makes it really simple to build your applications because all of a sudden you outsource all of this data toxicity to a single place where you can actually keep an eye on it and keep looking at it. And then you can employ strategies like, well, okay, like we'll actually encrypt all the data with, let's say, like a vault or a KMS keys and store it encrypted in a database. But maybe like we don't actually trust that, and we can actually then take the database and use its own encryption facilities, like CockroachDB, for example, supports encryption at rest, and also encrypt the storage disk that it's actually storing data on. And then we can be more certain that you have to actually compromise multiple systems in order to get access to that data. And if you think about security, it's all about defense in depth. Like the harder it is, ultimately, like a very sophisticated, determined attacker can overcome almost like any system you throw at them. So the more hurdles you can present, the more things that they need to overcome, and maybe like, at some point in time, it might be not worth it for them to pursue that angle of attack because like there's just too many things that they have to battle against.
So in your current role, you're the director of engineering that covers the KV engine. That's effectively our storage engine in CockroachDB, right? So how does that influence your work in actually enhancing CockroachDB at the storage layer?
That's an interesting question. So in my current role at Cockroach, if you think about it, Cockroach is a distributed database. We are built on top of a key value store. And so my team is responsible for everything that we have to do with that key value store and maintaining its distributed state across multiple nodes. And so I would say for us, what we do day in and day out is not too dissimilar of what we used to do when I used to work in the payment space. Like what we really obsess about day in and day out is the stability and correctness of our database, which is really the same obsession that you have when you're building a payment system. It's like the stability and correctness of your systems. Are you processing payments correctly? Well, are you processing transactions correctly? We're just kind of like moved down a layer and we're working directly on a database that allows you to build stable and correct systems on top of us.
So I know that, changing direction a little bit, we've talked a bit about how a lot of these systems end up using multiple different languages, right? Particularly if you've got a NoSQL database and a SQL database in kind of the same in the same environment. How do you kind of handle the difference in integration points, the difference in systems, and just the amount of mental gymnastics you need to be the technological equivalent of multilingual?
Yeah, I think that's an interesting question, Keith. My personal preference is not to handle that at all. And that sounds kind of like dodging your question, but I think that it's really not. If you think about it, there's this saying, you have to use the right tool for the job. And there's a lot of power to that statement. like certain systems like Cassandra maybe scale much easier, and they're much more available because they don't have transactions and they don't have to worry about certain data consistency guarantees versus like a Cockroach DB that's highly consistent and serializable. Certain other systems run better on a single machine, like a single node Postgres is always going to be faster than a distributed database because there's no replication overhead and you have to do distributed transactions. And certain other systems, for example, like, I don't know, Neo4j is better at graph workloads and things like that. And then all of a sudden, like you start thinking about, well, I have different needs for every different application I have. So I will just like really pick like the ultimately right tool for the job. And what you have is then you have this mishmash of technologies that you're running upon. And then what you then figure out from a scale and operations perspective is that as your business grows and as your transaction volumes increase and you have to do more things, it's kind of really hard to maintain all of those disparate technologies because they have different scaling challenges, they have different bug profiles, they have different operational profiles, you have to have different tools to maintain them. You then try to outsource it to your database group that kind of can maintain them all for you. The people on there don't really want to do it because it's just like too much mental energy to do that. And so what we see actually a lot of customers do is that they pick a technology that makes sense for their really like sensitive core, what we call like tier 0 workloads. And they're really happy with it. And then they say like, well, it may be not the ideal thing to use for this other workload, but it actually generally works well enough for that. So let's just use that because we're really good at operating that. And that what we see people do is kind of like adapt, try to go more single stack than multi-stack, because at the end of the day, like multi-stack, unless you have a DevOps team the size of Google, is really, really hard, just because like you have so many disparate systems running, and it's really hard to build operational competency in every single system that you have to operate that way. You're much better off building an operational excellence in one system and operating it really well, or maybe two systems, than having to spread yourself out thin like that.
And so how does that change the way you would build a modern payment system?
That's an interesting question. I think it changes the way that you would build. It kind of goes back to our earlier conversation of what is your kind of hierarchy of need as you're building an application. So I think where we left off that conversation last is that we were getting to this place where we were talking about sharding and kind of operating at a large transactional scale. And so the way that it changes is that if you have a technology available to you that handles that for you, then okay, like we've now, let's say, picked Cockroach DB and we're building a payment system on it, and it's automatically sharded for you, and it could scale really well within the one data center. Well, what usually happens next to the business after that? Well, at some point in time, your CEO is going to go and say like, okay, like we've cornered our market of country X, let's expand. Let's go to other countries. Let's go to other locales. Let's bring our great product to other people across the world. And then let's say Japan is the best market that fits right for us, and we're expanding out of the United States. And the first thing that you do, you go and you turn on your service in Japan, and then you figure out that nothing works and the customers hate you. And you're like, why does that? Well, all of a sudden you find out about this thing called the speed of light, and the fact that your transactions from Japan now have to travel to your data centers in America, and that round trip time is absolutely killing the responsiveness of your application, and nothing really works well. And so now you have to kind of go back to the drawing board. If you're in this like old MySQL world, well, now we have to kind of like put some MySQL databases somewhere in Japan, and we have to kind of teach the application that these are kind of Japanese transactions and things work over there and things work over here, and tie it all together somehow. Or you could use a technology that actually has native support for multi-region capabilities, and you can deploy just another region of that application, of that database, to that new market that you're going into. And then you could use the innate provided facilities of that database technology to say like, well, like if a payment originates on a Japanese server, then just like assign a little marker to it calling it a Japanese payment, store it in that locale. And for the US payments, do the same thing over here. And then if, for example, like we need to query data between the two of them, well, like you have a routing layer within the database that can actually take care of it for you. And what I've kind of like briefly described is how Cockroach multi-region works. And it makes it really easy for you to extend your capabilities to such a scenario, where before you would have had to probably spend, I don't know, maybe years, maybe months, or God knows how much time rebuilding your application in order to work like that. Or you could just say, well, like we're always going to have a crappy experience in that other country, and we're not even going to solve for that. You're just going to always go to our US data centers, and we'll try to do something at the application layer to make it a little bit more palatable to our users, which is
So
sometimes what people do.
you kind of led right into my next question, which was going to be around what's the right place to start planning, building that kind of payments processing architecture so that you can solve these problems outside of the database, which I think we both are pretty passionate about. What other areas of the architecture are really important to focus on early to make sure you don't run into the types of challenges you just described?
I think the actual most important thing that you can do to plan on early, and it's also really, really hard to do, is just really think about the data model of your application. And I know you asked me not to talk about the database, but like if you really want to focus on the thing that's most important, is that you can go to any real successful company, any Silicon Valley unicorn or like large bank or whatever it is, and look at their like core data model for the most important thing in their business, whether, like at Square, you could look at the payment processing data model, at BlackRock, at like stock transaction data model, or whatever it is. You will find that data model looks not identical, but like 80% the same as like the day 3 when the engineers just kind of like put it in place. It's now has more tables, more columns, but the general structure is always the same. You have, and the relationships that you define between the entities is largely the same and is unchanged. And the reason for that is that because once you get that structure in place, the momentum that you have and the growth that you have in your business and all of those other things, like they just overwhelm you. And you could start with a monolith, you could shard it into microservices, you can do all of those things. But at the end of the day, like the data model and like how the entities, like the user that relates to your payment, the balance that relates to your payment, like how that all is tied together is always all like it's the same. It might be in multiple systems, but the relationships are still there. And those relationships are the things that are going to constrain you the most, because if you have to do something that doesn't fit within them, you're going to have to do all kinds of weird mental gymnastics in order to change your data model where you have, like now 50 terabytes of data accumulated from the 10 years of your business to be able to do something. And so if like one word of advice I have for people is just to take like an extra 3 days, 2 days, a week, whatever it is at the onset of you're doing something, and just think through how you design your data model to be rigid but flexible. Like it has to be opinionated so it's easy to use, but you also kind of have to think about, like some of the potential things you might do in the future and leave a place for that in your model so that it's easier for you to bolt those things on years down the line. And I think like that's really the thing that's hard to think through in the beginning, but it's also like the most important thing to think through in the beginning, because a lot of times like that's the thing that limits or constrains you, and where, in the future where you have to do a project, it's going to be the difference between a project that's going to take 2 years to do versus a couple of months to do.
So once you have what's hopefully a good data model, and you've got a data layer that hopefully solves a lot of kind of the unnatural problems you're describing a little bit earlier, what do you build on top of that? And how do you think your way through which systems interact with the database directly, indirectly, and whatnot?
Yeah, I think it's a good question. I feel like there's no right answer. There's no right way to do it that's universally right. There's only trade-offs that you have to think about it. And ultimately, in the beginning, it's always better or easier to avoid, I don't know, like what's the easiest way to say it? Like early specialization. Like some people would say that, like you can't really, there's a reason why all the early Silicon Valley companies, they started as monoliths. And for a time, there were all these companies that started as Ruby on Rails monoliths, for example. It's just because it's so easy to get off the ground, and you have to do this like mental gymnastics of, well, we could really build this to like work for 1 million users, but we have 3 right now. So like, what's the right trade-off here? Do we build more features and kind of launch our product quicker, or do we spend all of this time on our architecture and figuring out, like how do we make this thing scale before we even achieve product market fit on our application? And so I think like it really comes down to how do you make the right set of trade-offs, and how do you figure out which decisions you can revisit at a later date and which decisions you can't. And so for example, the earlier one I gave you around the data model, to me, it's a decision that's really expensive and hard to revisit in the future. And so I think you have to look at every decision that you have about your architecture and figure out which bucket it falls into. Is this something that we can fix easily later, or is this something that's going to be crucial for us to get right today? And so I think a lot of times figuring out which applications connect to the database is like a thing that you could always revisit later. You could have more applications than you strictly need and share a database in the beginning because it might be easier operationally for you to get going, and tease that out in the future. But maybe some other decisions that you make about, which database technology you choose, which language you write your applications in, like some of the initial architecture choices are going to be much, much harder to revisit in the future and will require multi-year migrations that you'll have to do in order to get right.
So before I throw it back to Eric, were there other topics that you wanted to talk about with the attendees here today?
No, I'm curious to hear what questions people have, and maybe we can try to weave in something that people are interested in into our conversation.
Yeah, Eric, I'll throw it over to you to see if you have any questions for Alex.
We did get a number of questions, so let me switch over to my list and let's go through them. All right, so one of the questions came in here which says, could you please expand more on CDC, how it works, and what are the pros and cons?
Sure. So I think the easiest way to start is maybe to actually explain what CDC stands for. So CDC stands for Change Data Capture. And so the way that CDC works within CockroachDB is that it's natively built into the product. And so as you write data into the database, we keep track of, the easiest thing to think of it as like, we keep track of the transactions that have been committed. And then on a per logical model structure, so let's say a table, we can kind of say that, okay, like you've now inserted, let's say 10 rows into the table. We can actually publish those 10 rows to an event bus of your choice. And that all happens in a sense transactionally. So what that really means is that if you have a complex transaction, the easiest one, let's say like, you record a payment, you update a balance table somewhere, you record some metadata around the payment. And so like maybe your payment transactions in and of itself actually has to commit to 7 different tables. And so what will happen is once that transaction commits, that data will become available for the change feed to then go and publish it to your Kafka or to your Google Pub Sub. And so the difference between that and doing that yourself is that suppose you're building this application and your database doesn't have a change data capture capability. And so then you can think about writing this code in your application that says, okay, like commit this transaction to the database. Once the transaction is committed, publish this event to Kafka or my message bus and processing logic. And so that all works great up until your server crashes right after it commits the transaction, and you don't get that event published to Kafka, and then all of a sudden, like you have subtle breaks in your application because the data never made it there. A database like CockroachDB that has change data capabilities, naturally, like once you press that commit button into the database, it kind of takes over, and it will make sure that that event makes it to Kafka no matter what happens. And you could say like, well, Alex, I'm gonna outsmart you. I'm gonna actually like change this and like put the Kafka commit in front of the transaction commit and publish the event first to make sure we never lose the event. Well, like that's great, but then you publish the event and your server crashes right after that, and the transaction never commits. So like the payment never happens, but the event published, and maybe your event is sending like a push notification to your user that says, hey, this thing happened, which actually never did. And so now your application is kind of broken in a different weird way. And so then you have to we talked a little bit about this before. You have to then build some kind of like two-phase commit logic to actually make sure that something committed to your database, committed to your event bus, which is all very hard and very complicated. And as a developer that's focused on building a payments application, I'd rather probably not bother doing, because there's people that already solved it for me with these technologies like change data capture.
Yeah, so that actually steers into one of the other questions. I'm going to move through them in a different order here. How would you still guarantee a transaction happens when outside the database system landscape?
Not sure I follow that question altogether, but maybe I will try to answer it to the best of my understanding. And so one of the things that you have to think about building payments applications is that a payments application doesn't exist in a world by itself. It exists within some broader ecosystem. And what I mean by that is that it's not typically enough to record something about a transaction happening in your database. You typically have to send, after that, you have to send a message to some other party to say that, like, well, I recorded it in my database, so now I have to send a message to like a payment acquirer to say, like, actually process this credit card transaction, or to some money movement service and say, like, actually move this money. And so typically the way that you have to think about it is you have to think about it in terms of queues. You have to build a queue somewhere in your database. You can build it somewhere into your application, and you can build it into your database, you can build it into your application, and basically you have to say that, hey, now I have to send this message. I have to guarantee that that message was received, and I have to record some state about it when it actually gets back. And if it doesn't, then I have to build a retry loop somewhere in my application that actually keeps retrying all of this. And that's all could be quite difficult. And so one of the ways that we've solved this in the past is that we actually use change data capture for that. We could say that, like, hey, you recorded this payment in our database. We'll actually publish an event to the service that is going to go out and guarantee that it actually sends it downstream for processing to this other application. And we will, let's say, put the payment into a pending status in our database. And then eventually, when that succeeds, it can go up and update it and say, hey, it was actually processed. And you actually have your Kafka queue or your PubSub queue keep retrying to process that event until that external system becomes available and can actually process it.
One of the great things about having full transaction support in CockroachDB is you can do this pattern called the outbox pattern, where you record both the transaction to the transaction journal in the database, as well as record a record to an outbox table that handles that mechanism that Alex just mentioned. And you can do it in the same transaction, so they both are committed at the same time. And that allows you to externalize that logic that they were asking about, Eric, while keeping the transactional consistency in the database and being able to track whether or not a message got consumed separately from the actual raw record. We have some great docs on it if anyone on the call is interested in researching that more.
That's pretty cool. I didn't know about that. And I've seen a lot of systems that get out of sync because they can go at a commit and then it's a queue from elsewhere. So speaking of queues a little bit, there was a question of, is it possible to have multiple subscribers listening on the same message from the publisher? So you've got one queue and one routing key and all the subs are listening onto the same binding.
That's really not a limitation of the change data capture technology in CockroachDB. It's really a limitation, or sorry, a capability of the system that you're publishing to. So most of our customers use CockroachDB together with Kafka, and so they publish their events to Kafka. And in Kafka, you can have as many listeners as you want, and like the listeners are rather independent of the publishers, which, for example, compared to Amazon SQS, if I get my facts right, when you publish a message on SQS, like a consumer consumes it and it's gone. And so therefore, like there's a difference between those technologies, and it really depends on which sync you choose to use and the capabilities of that sync.
All right. One of the other questions in here is, what's the advantage of storing keys in a database like CockroachDB instead of using a secrets management system like HashiCorp Vault?
I
don't
don't. Go ahead,
I
Keith.
don't think you would actually store the keys in CockroachDB, right, Alex?
No, you wouldn't. Typically, you would rely on AWS's KMS or Vault or something else, and have the experts kind of deal with it for you.
All right. Here we go. And it was a clarification question of, when you talked about sharding, do you mean with CockroachDB, is it possible to have the same database split into different regions? For example, the same database where some records are stored in China and some other records are stored in the US?
Yes. So the easiest way to think about it is that CockroachDB offers you a few easy to follow constructs to build your applications. And those constructs are twofold. One is we have a concept of what we call a global table. So the easiest way to think about it is that a global table would be something like discount codes for your application, where you might have 100 discount codes that are shared across the world that offer you savings when you perform some kind of transaction in your system. And the key feature about discount codes is they're read really frequently across all of the regions for your application, but they're written very infrequently because it's a small data set. And so for those, what CockroachDB will secretly do underneath the covers, it will kind of spread a replica for that table to be present in every single region. So when you try to do a read, that read is super fast because there's data in that region already for that small table. And that allows you to build easily shareable global reference data. And then you can think of like, well, your payments table is really not like that. Well, your payments table is more, hey, like transactions that are happening in Japan are only happening in Japan. The ones that are happening in France are happening in France, and the ones that are happening in the US are happening in the US. And so for that, what CockroachDB offers is it offers a regional by row capability. And so you could specify the region of your transaction yourself through SQL, or you can let CockroachDB take care of it for you. And so you don't actually have to say what the region of the payment is. Depending on the gateway that you use to access the node, it knows where it's running. So the server knows that it's physically located in France or it's physically located in Japan, and it will stamp itself onto the record, and it will say like, hey, I'm saving this record for Japan or for France or so on and so forth. And like physically what happens underneath the covers, you can think about it, is the CockroachDB has a replica just for the Japanese payments in the Japanese region, just for the French payments in the French region, and so on and so forth. And so it can actually store that data in the region where it's happening. And then you could actually then go in and modify those patterns to your content, and you can actually say like, well, actually I want the French data to be replicated here as well, or maybe we want to say occasionally we would love to read French payments in the US because we have multi-regional users, so we can actually store replicated state information about that there. And so you actually have a lot of control over how the data gets placed and replicated around your cluster with CockroachDB without having to do it manually that you would in a manually sharded scheme like MySQL or something like that.
Yeah, there's some trade-offs between performance and availability that you have to manage, and of course there are compliance things that you have to think about too when you're talking about running across multiple jurisdictions. But because CockroachDB offers you the ability to declaratively describe for kind of each pattern how you want things to be distributed across the environment, it becomes a very powerful way to build a global application in a single logical database.
All right, and for people who build applications on top of CockroachDB, how do they release new versions of their code, like major versions that have a schema change and minor versions that don't, and just manage migrations?
That's a good question. So CockroachDB natively supports schema migrations. So you can run alter table, alter index statements. And typically we see people package them up into like a migrations manager. So for example, for the Java developers out there, a lot of people use Flyway. So you would just deploy, it really depends on how you architect your changes. So typically the way that I've done it in the past, and it's not different with CockroachDB, is you put your migrations in place and you deploy your database migrations first. And then you make sure your code that's currently, the migrations are backwards compatible. So for example, you add a nullable column and you let that deploy. And CockroachDB supports online migration. So what that means is that your transactions are still running, and behind the scenes, Cockroach is going through and it's adding that column. So you added the nullable column, you then deploy your code, you start using that column, and maybe you run some backfill script to populate it with some data. And so now there's data in all of that column. So now you can go ahead and run a migration to say like, okay, like we're gonna make this column non-nullable because there's data in it. And it's there and it's great. And so maybe you want to then remove a column. So now you deploy code that stops reading that column, and then you go in and you drop it. And so you kind of have to always do it in a backwards compatible way, because there's no way to atomically deploy both your application and the database at the same time. The only way to do that, and it doesn't really matter whether you have online schema migrations or not, is to shut everything down, do the deployment of both things at the same time, and kind of bring it all back up together. And that's probably not what you want to do with modern applications that have always on requirements.
All right, there are two questions in here that I'm going to combine a little bit. One of them said, can we talk more about system architecture? And the other one said, where can I get more information to learn about payment architecture system, such as any books? So like, does Cockroach Labs have a repository of knowledge base of effective patterns, or are there places that you look for guidance of similar systems?
So we have a bunch of docs, lots of blog posts. We also have an O'Reilly book, The Definitive Guide to CockroachDB. I think those are probably we also have Cockroach University, which is kind of online training that's self-paced. Alex, can you think of any other resources that folks might?
I think the best resources for payments applications specifically is when we began this presentation, there was a slide that you showed, Keith, and then we're going to distribute the slide hopefully after this presentation, and people can take a look at the links there. And there's some case studies to successful customers that have used CockroachDB to build payments applications. And there's also some links to some reference architectures that we've developed. And so those are probably the best places to start out of the content that we provide.
Great. Another question here is, how do you manage to have a very large database with terabytes of data and keep it responsive? Do you just keep increasing the disk space, or is there a limit on Cockroach, or is there a way to move old entries to a cold storage?
That's an interesting question. And so the easiest answer is we have a recommended what we call node density size on Cockroach. I believe right now it's at 10 terabytes. So if you think about it, like you want to have one node, and we roughly recommend that you don't exceed the size of 10 terabytes of disk on that one node. And so typically what we see customers do is they start out and they say like, they say for our transaction processing needs, because we process X transactions a second, we need 9 16 vCPU nodes, and we run those. And then if you see your transaction processing needs increase or your disk spaces fill up, you just add more nodes, and the system underneath the covers will say like, oh, I have more nodes now. I will just like move all the data around to have an equal balance of data across all those nodes. And so you can do that in perpetuity. Obviously, like at some point in time, it might get too large. We haven't really run into that with customers yet, but it's also, you could be like, well, I don't really want to pay all that much for data I'm not reading. And so today you kind of have a couple of options. One is we have this really cool feature, which we call TTL, which is time to live. And basically you can go to your table and you can specify like the time to live for this table, let's say like 90 days. And I only want to keep 90 days of data around. And so after that, CockroachDB will automatically delete the data. well, like, that's great. The data is being deleted, but like, where do I keep it? And so what we see a lot of customers do is we see them actually hook up CDC to their cluster, and then they export their data to some colder storage through CDC, and they delete it out of the main processing cluster using a TTL feature. You could also, that's kind of what we have today. It's a topic that we're actively thinking about it, but I'm not really prepared to say that what we're going to do about it in the future.
I think the important thing to keep in mind is because we're a distributed database and we automatically manage the data sharding, and nodes declare their location in the topology in the cluster when they get started up, you can always scale your way out of those types of problems with CockroachDB, whereas that's not necessarily true with a legacy SQL database.
Got it. All right, in that case, we're at time. So thank you both very much for the great discussion about payment systems.
Thank you.
All right, thank you very much, everyone, for watching, and we'll send a copy of the recording out as well as a copy of the slides where you can get some extra links and resources. Have a great day.
All right.